All right, so welcome to this video where we are dealing with a slightly more involved miscellaneous equation on differentiability. So we are given f of x as that particular function piecewise. It says determine the values of a, b, and c so that f of x is continuous and differentiable. It is exactly like that, everywhere differentiable, everywhere continuous. So there are just a few things that we need to do when approaching this question. So what I would do or suggest is that whenever you're approaching questions of this type, what I essentially advise you do is sort of like draw up a line there and focus on the critical value. So we can clearly see that one of our essential values is -1. And then there's what happens between -1 and 0. So I would put 0 there. And you can just work out. So if you're approaching -1 from the left, the function we bump into is exactly this one over here. All right. And in between, we've got the function x squared plus bx plus c. And on the other side of 0, what we do have is x squared plus 2x plus d. All right, so this makes our jobs a little bit easier. So the first thing you want to do normally, we have to solve for these variables, is to start with differentiability. All right, I'll put a D there for differentiability. And what the differentiability allows us to do is to do this. So if we are approaching, so the limit of the derivative now, because we're using differentiability, so we will go with the limit of the derivative. And that's what I will start taking first if we're doing differentiability. So maybe let's remove that. Let's go as x tends to 1 from the left. We'll take the derivative of this. So the derivative of that becomes 2x plus 6. Similarly, if we take the derivative as we tend to -1 from the right, the derivative of this is 2ax plus b. And then again, if we're looking at 0 again, if we're going to take the limit of this as we're approaching 0 from the left, so this we take the derivative of that expression again, plus b, and also we take the limit as you're approaching 0 from the right, and the derivative of that is 2x plus 2. So what we then want to do is substitute our limits. So I'm going to start from this side of 0. So if we substitute our limits, that becomes 2a times 0 plus b, leaving us with just the b on the other side. And on this side, we know that by differentiability, these sides must therefore be equal, whatever at the point that we're dealing with. So again, if we take the limit of this, this becomes, we're substituting 0 wherever we find x, and therefore this gives us 2. So already from here, we can come up with the conclusion that b is equals to 2. And I'll just highlight that. What a nice question. So now let us, we find b is equals to 2. Let us go back to this side. This side, we then need to substitute -1. Remember, we were approaching -1. So therefore, in our next line, we'll have 2 times -1 plus 6. And we can work that out to give us 4. And on this side, we'll substitute -1. So this is 2 times -1 plus b, therefore giving us minus 2a plus b. But remember, we had just worked out what b is from our previous example. So therefore, we can safely say this is minus 2a plus 2. And therefore, by our rules of differentiability, we can say that 4 is equals to minus 2a plus 2. And then from here, if we work it out there, we can easily work out that a is equals to -1. Bam. So that is our other value. We found a is -1. So continuing with this diagram again now, I will just use a blue pen just to differentiate this. We're still continuing. We'll now use continuity. So remember now in continuity is that the limit as x tends to -1 from the left will give us that function that we find there. So I'll just simply rewrite the function as it is. And then on this side, if we are taking the limit as x tends to -1 from the right, we are bumping into this function now. We will now substitute our limits as we go on. And similarly here, if we are trying to find the limit of 0, we are getting again into the limit as x tends to 0 from the left. we are getting into x squared plus bx plus c. And similarly, again, on this side, if we go in with continuity, the limit as x tends to 0 from the right becomes x squared plus 2x plus d. So we do know that just at the various points, we'll have equality there. So again, if we then substitute what our limit is again there, we will get minus 1 squared as just 1. We'll get minus 6 there. We'll have plus 5. And then on this side, if we're substituting exactly what our limit is there, we will get a positive a, and then we'll get a minus b plus c. But if you look at this, right, it means that this left-hand side will equal to that. So 0 will equals to, if we substitute a and b that we found, this is minus 1 minus 2 plus c, then we can easily work out that c is equals to 3. So let's try use a different color for that. C is therefore equals to 3. So slowly but surely we are breaking this and finding it because we're focusing on these variable points. Let's look again at the point 0. If we're approaching 0 from the left and we're substituting there, so we have a times 0 and b times 0 plus c. And therefore we just left with c on the other side. And similarly, if we substitute 0 there, we get 0 plus 2 times 0 plus d, and therefore we get that d is equals to c, but c was equals to 3, so therefore we get d is equals to 3. Bam! So there we have found all of the values that we're looking for. So a is negative 1, b is equals to 2, c and d are equals to 3. So this is how you then approach a question of this type. This is a nice miscellaneous equation checking differentiability. Make sure that you use continuity where you can and use differentiability where you can. I hope this has made sense, and therefore I hope that you've enjoyed it. See you in the next video.